Hi guys, this is James, and today I'd like to discuss the receiver operator characteristic, which is definitely one of the danker methods you'll encounter in your statistical pilgrimage. The receiver operator characteristic actually has quite an interesting history, in that it was originally developed in World War II as a way to determine whether or not an object on a radar output was an enemy, a friendly, or just white noise. As a statistical method, it has gone from its original use as a tool to determine whether an object should be shot at with artillery to determining the effectiveness of medical screening techniques. As you know if you've been watching my videos, I am fascinated by the universal applicability of statistics and the context in which the ROC curve was developed compared to those contexts in which it is used today does well to illustrate this. So, the receiver operator characteristic is an indicator of how effective a continuous variable is at predicting the outcome of a binary variable. As an example, we could use the weight of a coin to help us predict whether it lands with heads or tails facing up. It is often believed that most coins have a 50% chance of landing on either side when spun on a table. However, some coins are heavier on one side than they are on the other, which means they are more likely to fall with that side face down. For example, American pennies have close to an 80% chance of landing with heads face down, because that side weighs much more. So, if I were to take the weight of one side of a coin and see if this would help me predict which side lands face up, I could use the receiver operator characteristic to provide an indicator of how well this weight predicts my coin spins. Now let's say that I have a univariate weight distribution here, and at the base I have a weight of 0 grams, and up here I have 20 grams. So, in order to build the receiver operator characteristic, what I start by doing is saying, okay, at 0 grams I'm going to predict that all my results are tails. And in this way I'm setting a cutoff value at which I will predict what all my results will be. So now I'll slide this cutoff indicator up and say, okay, at 1 gram I'm going to predict that all my results are tails. And then at 2 grams and 3 grams and so on and so forth until I've slid through the entire distribution. Now let's map the probability distributions of achieving a positive desired result and a negative undesirable result onto our weight distribution, like this. So, we're theoretically adding a y-axis that represents probability, and each of these normal distributions represents the complete probability of achieving a positive desired result or a negative undesired result. So if I were to predict that the coin would come up as tails, then the area under this green normal curve represents all the different probabilities of this occurring at different weights. Similarly, the area under this red curve represents the complete probability of achieving heads, our negative result. Now, if I pick this weight value here as a cutoff, this means that every result above this cutoff I am going to predict as a positive result, even if it's not. And every result below my cutoff I am going to predict to be a negative result, even if it is not. And any guess that is wrong can be labeled false, while all my correct guesses I can label true. Accordingly, I've coded our negative and positive distributions so that blue represents all true results and yellow represents all false results. And in this way, I will have true positives, true negatives, and false negatives. If we take a look here, we can see that this small end of our positive distribution extends below our cutoff value, so these are positives that we will be guessing to be negative. And at this end, the negative distribution extends above our cutoff value, so we will be guessing these to be positive when really they are not. Now, I'll switch back to this previous color coding, and I'd like us to think about all our positives as a proportion. So all results that fill this area under our curve equate to 1. Likewise, we'll think of our negatives as a proportion too, and the area under this curve also equates to 1. Now if I start with a cutoff at the bottom of our distribution here, I am going to capture all negatives as false positives and all positives as true positives. So my true positive rate is 1 and my false positive rate is 1 as well. If I slide my cutoff up here, I am now capturing less I'm now capturing a lesser proportion of false positives, and I'm still capturing all positives as true positives. So my false positive rate has dropped to 0.65, and my true positive rate is still at 1. And if we push our cutoff up to here, we now have approximately 0 false positives and 0.50 true positives. Now, if you think about how these two values behave as a function of each other, we can plot their relationship using a simple dot plot. To illustrate this, I will now present the receiver operator characteristic graph. On the y-axis we have the true positive rate, while on the x-axis we have the false positive rate. Now if we were to graph the true positive false positive rates that we achieve as we slide our cutoff through our distribution of weight, we would simultaneously be mapping a curve onto our receiver operator characteristic graph. Diagonally, a line divides our graph in half. If a point falls above this line, it has a true positive rate that is higher than its false positive rate, which distinguishes it as a good classifier. If a point falls below this line, then the false positive rate is above the true positive rate, which still means that our model is able to discriminate between results effectively, but just not in the direction we were hoping for. A point that falls right on the line suggests that our continuous variable is incapable of distinguishing between results, and thus doesn't help us in guessing our outcome. And in this way, the receiver operator characteristic provides a complete picture regarding how well our continuous variable is able to predict our binary outcome. It is not a metric that evaluates any one particular cutoff, but gives us an evaluation of all cutoffs simultaneously. If I bring back this graph I showed previously where we were sliding our cutoff value around, you can see exactly how this distribution relates to the receiver operator characteristic curve. As I slide this cutoff up or down, the point on the curve moves up or down as well. And in this way, the receiver operator characteristic provides us with an interesting metric regarding the discriminatory power of our model. Specifically, how well a continuous variable is able to predict a binary variable. In our specific example, how well the weight of the head side of a coin is able to predict what side the coin lands on. Now, the receiver operator characteristic is often referred to as ROC, or ROC for short, and you can request it as a diagnostic for logistic regression models in most statistical software packages. I've found it useful for giving me a fresh look at my model. Sometimes it's hard to decipher what use your logistic regression model has, and the ROC curve can give you a slightly different interpretation. I was actually first introduced to the ROC curve by a colleague. I mentioned that I was having some difficulties appraising the appropriateness of a logistic model I'd built, and that the diagnostics I normally relied on were not behaving in ways I had ever seen before. He suggested I check out the ROC curve to see if it would help me understand what was going on. I hope you have enjoyed this video, and thank you for watching.